So yesterday we discussed that the relation between MA and VR. Okay, and we found that the efficiency is MA upon VR. Okay. Then we were talking about the most important thing about the actual and ideal machine. In actual, you will always find that the MA of all the machines is less than its VR. Okay, you will always find that MA is less than its VR. Okay, and this is the reason why you find that the efficiency of a machine is not 100%. Okay, so we have seen this table. Okay, this is an just example to explain you what exactly happens in ideal and actual machine. Okay, so assume that if in an ideal case the MA is 4, so the VR will also come out to be 4. So you will find that the efficiency will be 1 or 100%. So the efficiency of this machine, an ideal machine, is always 100%. But if the same machine is used in actual, you will find that the VR parameter still remains the same. The VR, the velocity ratio of an ideal machine or an actual machine, remains the same. So what changes? So you'll find that the MA of it is being reduced. So the MA is 3 and VR is 4, and that's why the efficiency of this machine comes out to be 75%. Okay, so this is what we have discussed yesterday already. Okay, now let's start with what the next topic. And since we are quite familiar with all the terms associated with machines, we have seen right from the beginning, we have studied what is load, what is effort, then what is MA, what is VR, work input, work output, efficiency, and then the relation between MA, VR, and efficiency. So now our technical terms are clear. Let's start with the topic, the first type of machine in our syllabus, and the machine in our syllabus is levers. So basically, what is lever? So something like this, we had already studied about levers in principle of moment. So a lever is nothing but, if you try to define a lever, it is a rigid, straight, or sometimes bent bar. Okay, what is lever? It is a rigid, it is made up of a rigid material. It is straight, or sometimes you will find the lever is bent as well. Bar which is capable of turning about its fixed axis. And the interesting part of lever is it is capable of turning about its fixed axis. Okay, and the point, the axis along which it rotates, is called as fulcrum. And then we place a load at one end of it and we apply the effort at other end. So this is what we are quite familiar with lever. Okay, so this is how the definition of a lever goes. Principle of lever. On what principle it works? So we have again studied this, that a lever works on the principle of moment. You remember in the first chapter we discussed what is principle of moment. The principle of moment says in equilibrium the sum of clockwise moment is equal to the sum of anti-clockwise moment. So on the same principle you will find our lever also works. So the lever works on the principle of moment, and according to that principle of moment, the sum of clockwise moment is equal to the sum of anti-clockwise moment. Now we have just framed this in terms of clockwise moment of load is equal to the anti-clockwise moment of effort. Exactly. So there is a load due to which it produces a clockwise moment, and we apply the effort, and due to which the anti-clockwise moment is produced. But again, the clockwise moment of load will be equal to the anti-clockwise moment of effort. Now, the very important point what you have to understand, because we are using the principle of moment, but we are going to use some more terms in it. Okay, so you should know about these two very important terms. Okay, the first important term you should know is what is fulcrum. So fulcrum is nothing but a point where the lever will rotates on its axis. So that's our fulcrum. Okay. But the another very important point is what is called as load arm and what is called as effort arm. Okay. So the distance between the load and fulcrum is called as load arm. So understand, whatever the distance we have from the load. So this is my load. So from here till the fulcrum. Okay. This is my load. This is the center of gravity of the load. So from here till the fulcrum, this is the distance. So what we call this distance from the load till the fulcrum, we call this distance as load arm. Okay. So remember, the distance from the load to the fulcrum is nothing but our load arm. And the distance between the effort and fulcrum, or from the effort to the fulcrum. So understand, where is the effort applied? So the effort is applied here. So from here till the fulcrum, this distance from the effort till the fulcrum is my effort arm. So you have to understand what is load arm and what is effort arm. This distance can be described as load arm. In short, I can write LA, load arm. Okay, and this distance can be called as effort arm. It is, in short, I will write EA, effort arm. So understand what is load arm and what is effort arm, because every now and then we are going to talk about load arm and effort arm when we are talking about levers. The only important point I want all of you to understand here is that it is a distance between the load and the fulcrum. So important thing you have to understand that whether you define load arm or whether you define effort arm, it is always from the load and to the fulcrum. From the load to the fulcrum, or from the effort to the fulcrum. Okay, so understand what is necessary. So we are always going to measure the load arm or the effort arm from load to the fulcrum, or from effort to the fulcrum. Okay, so don't get confused here with this, that your load arm is from the center to the load or from one end to the other. No, it is always going to be, we are going to measure the load arm and the effort arm from fulcrum. Okay, so remember what is load arm and what is effort arm, because this is something again we are going to use so often. Okay, so this is how this is one type of lever I have shown you, where I've shown you what is the load arm and what is the effort arm, the distance. As I had already told you, okay, that it works on the principle of moments, where the clockwise moment is equal to anti-clockwise moment. Now this clockwise moment and anti-clockwise moment is been reframed as clockwise moment of load is equal to the anti-clockwise moment of effort. Now remember, what was the definition for clockwise moment? How we were measuring clockwise moment? So we were taking force into perpendicular distance from the line of action of force to the axis of rotation. If you remember how we were defining clockwise moment or anti-clockwise moment. So we were defining the magnitude of force into the perpendicular distance from the axis of rotation. So the same thing here is being represented in a different way. So clockwise moment of load. I told you what is load. Load is nothing but the force which the machine has to overcome. So obviously the clockwise moment of load is load. The clockwise moment of load will be force into perpendicular distance from the axis of rotation. So here, what will be the force in that case? The force will be load. And perpendicular distance from the axis of rotation is nothing but your load arm. Okay, so see, the same statements is been reframed. So clockwise moment of load, since load is a force, so I am saying force into perpendicular distance. So for force, I am using the word load, and perpendicular distance from the axis of rotation, if you figure it out, it is nothing but it is your load arm. Okay, so what is the clockwise moment? this force. If you recollect properly, it is this force into this distance. This is my clockwise moment. This force load in a downward direction to this distance from the fulcrum to the load, that is my load arm, is equal to what we apply, effort. What we apply is effort. So this is the effort. Okay, this is the effort, and this is our effort, and this is the distance which we call as effort arm from the effort to the fulcrum. So it's the same rule, just we have renamed the terms in it. So we found that according to the principle of lever, we get load into load arm is equal to effort into effort arm. Okay, so now I am rearranging these terms. So I say load upon effort. I am just shifting this effort from right hand side to the left hand side. So it's in multiplication, it will go in division. So it becomes load divided by effort is equal to effort arm, which is already on the right hand side, and this load arm, which is on the left hand side, goes, and it's in multiplication to it goes in division. So just a rearranging of the terms. So we get load divided by effort is equal to effort arm upon load arm. Now here you will find effort arm upon load arm. So what is effort arm upon, what is load upon effort? If you recollect, we had this very fundamental definition of MA. What is MA? It's a ratio of load to the effort. So if I replace this load divided by effort as MA, so I get a new formula for MA of a lever. And this formula is nothing but MA is equal to effort arm upon load arm. This very formula is the base for understanding the levers. Okay, so we are going to use this very important formula to find out the MA of a lever. What's the formula? MA is equal to effort arm upon load arm. If someone asks you from where this formula came into existence, so you have this very basic rule behind it, because a lever works on the principle of moment, and according to the principle of moment, the clockwise moment is equal to anti-clockwise moment, and then we conclude that our MA is coming out to be effort arm upon load arm. So this is the formula we are going to use to find out the MA in terms of effort arm and load arm. Even we can use the formula load upon effort, and we have the same formula for velocity ratio. What is that? Displacement of effort upon displacement of load. So this is the very basic and a fundamental formula we had for levers. Now look at it. Let's try to understand this idea, this very basic idea. Okay, now assume that if my effort arm is equal to load arm, okay, if there is a lever in which your effort arm and load arm comes out to be same, so what will be the MA of your lever? So the MA of your lever will be same. Why? Because what is MA? Effort arm upon load arm. So if your effort arm and load arm comes out to be equal, then effort arm divided by load arm will be 1, and that's why your MA will come out to be 1. So you can have this example here, that if you look at this distance, if you look at this very important distance, you will find this is the fulcrum, this distance is my load arm, and this distance is my effort arm. Because what is effort arm? From the effort to the fulcrum. What is load arm? From the load to the fulcrum. So if this comes out to be equal, my MA comes out to be 1. The same way, if my effort arm is greater than load arm, how is it possible that the effort arm is greater? Let's look at the effort arm. From where we define effort arm? From the effort to the fulcrum. So this distance from the effort to the fulcrum is my effort arm. And what is load arm? From the load to the fulcrum. So you will find in this very important case, your effort arm comes out to be bigger than the load arm, and here you will find your MA is more than 1. And the third possibility we have, that if my effort arm is less and my load arm is more. So which is your effort arm? So this is your effort arm. From the fulcrum to the effort. This is your effort arm. And what is your load arm? From the load to the fulcrum. So this is the load and this is the fulcrum. So you find in this very important example that your effort arm is less and your load arm is more. So if you calculate MA with the formula of effort arm and load arm, your MA will come out to be less than 1. Okay, so remember we have in levers, we have these three possibilities where my effort arm may be equal to load arm, effort arm may be greater than load arm, and my effort arm may be less than the load arm. Now we will categorize, we will find out the different types of levers. Okay, so remember the formula of effort arm upon load arm. It will help us to make the things very easy for us. So there are three types of levers. We start our discussion with the first type of lever, class 1 lever. Okay, now what you observe in class 1 lever. So this is an example of class 1 lever. Now, how will you identify a class 1 lever? So you will find that in a class 1 lever, the pivot or the fulcrum, it can be also called as pivot or it can also be called as fulcrum. So you find that the pivot or the fulcrum is in between, the load and the effort. So understand, in class 1 lever, you will always find that your fulcrum is somewhere in between the load and the effort. So whenever you find the fulcrum in between, listen carefully. I am saying in between. I am not saying in the middle. I am not saying in the center. Okay, it is not necessary the fulcrum has to be exactly in the middle of the load and the effort. Yes, but it has to be in between the load and the effort. So if we are having a lever, if you find a lever where the fulcrum is in between the load and the effort, we categorize such type of levers as class 1 levers. Okay. Now, what is the interesting part of this class 1 lever? Here, you will find that the effort arm can be equal, can be equal to, can be equal to or less than or greater than the load arm. Okay, now understand how is it possible that your effort arm can be equal to or less than or greater than the load arm. Okay, see, first of all, this distance from the this distance from the effort to the load, this distance is my, from the effort to the fulcrum, this distance is my effort arm, and from the load to the fulcrum, this distance is my load arm. Okay, so we have an option where your fulcrum is in the middle, and that's why your effort arm and load arm is same. But the same fulcrum can be shifted towards the left or can be shifted towards the right. And assume if you shift this fulcrum, assume if you shift this fulcrum towards the right. Assume I shift this fulcrum here. The fulcrum is now towards the right. Okay, so what will happen if the fulcrum is shifted towards the right? So you will find that your effort arm will be more and the load arm will be less. Okay, so that is one possibility. Or if you shift your fulcrum towards the left, so what you will find? You will find that your load arm will be more and the effort arm will be less. So when we have fulcrum in between the load and the effort, we have all the three possibilities. What do we have? We have all the three possibilities where your effort arm can be equal to the load arm, or your effort arm can be greater than load arm, or your effort arm can be less than load arm. And so you may find out that the MA of class 1 lever can be greater than 1, equal to 1, or even less than 1. So you may have to remember this very well, that the MA and the VR, understand, the MA and the VR of class 1 lever can be either greater than 1, less than 1, or equal to 1. Means if we have a class 1 lever, my class 1 lever can work as a, my class 1 lever can act as a, can work as a force multiplier. Why it will work as a force multiplier? Because there is a possibility that my effort arm becomes more than the load arm. If my effort arm increases and my load arm is decreases, or my effort arm is bigger than the load arm, then technically, mathematically, you will find that the MA will be more than 1. And if the MA is more than 1, then your class 1 lever will act as a force multiplier, or it can also act as a gain in speed or speed multiplier. How is it possible? You know very well that if the MA and VR is less than 1, if your MA and VR is less than 1, then your machine is a gain in speed. And how is it possible to have MA and VR less than 1? In that case, you need to have your effort arm smaller and load arm bigger. So what you will do, you will shift the fulcrum. What you will do, you will shift the fulcrum, the pivot, towards the left hand. And what you will find if you shift it, assume it is shifted from here, this very point, to this point where I have pointed the arrow. So you will find in this very case, the load arm will be bigger. This will become your load arm, and this will become your effort arm. Yes, so your load arm will be more and the effort arm will be less, and then you will find your lever is working as a gain in speed. And we do have the third possibility as well. We do have the third possibility, that is change in the direction of force only. When this is possible when your MA and VR is equal to 1. Okay, and when it is possible if your fulcrum is at the center, is exactly in the middle of the load and the effort. If your fulcrum is in the middle of the load and the effort, then exactly at the middle of the load and the effort, then you will find your effort arm and your load arm. Your effort arm and your load arm is going to be equal, and in that case, your MA will come out to be 1, your VR will come out to be 1, and the most important thing is that your machine, your lever will work as the change in direction of force only, or it is used, or it can be act as a change the direction of force only. Okay, so very important thing about class 1 lever, the very important thing about class 1 lever is that my class 1 lever can act, my class 1 lever can act as a force multiplier, as a gain in speed, or it can also act as a change in the direction of force only. It can have, my class 1 lever can have all the 3 possibilities. Remember class, my class 1 lever can have all the 3 possibilities. Now let's talk about the second type of lever. Okay, and what is that? That is our class 2 lever. Now what we observe in class 2 lever, how will you identify the class 2 lever? So you will find in class 2 lever, your fulcrum is at one end and the load is in between the fulcrum and the effort. Understand this arrangement, wherever you find that the fulcrum is at one end and the load is in between the fulcrum and the effort, such type of levers are called as class 2 levers. Okay, remember what we observed in class 1? We observed the fulcrum was in between the load and the effort. Here you find the load is in between the fulcrum and the effort. Okay, so in this case, what are the possibilities? Our class 1 lever was having all the 3 characteristics. It can work as a force multiplier, it can work as a gain in speed, It can even work as a change in the direction of force only. But let's look at it. What is the possibilities we have in class 2? Okay, let me recollect you that what is the load arm and what is the effort arm. So from the fulcrum to the effort, this distance is called as effort arm, from the fulcrum to the effort. And from the fulcrum to the load, this distance is called as load arm. So remember the distance of load arm and effort arm. Now, if you look at class 2 lever, you will come to know that class 2 lever, you will always observe, there is no change in this condition. You will always find that your effort arm is greater than the load arm. This is something which you are going to find every now and then, that your effort arm is greater than the load arm. And so you will find the MA as well as the VR will always be greater than 1. And whenever your effort arm and load, whenever your MA and VR comes out to be greater than 1, then your lever will only and only act as a force multiplier. Can it work as a gain in speed? No, because to have a gain in speed, your load arm has to be bigger than the effort arm. But here the arrangement is in such a way we cannot have our effort arm bigger than load arm, because the load lies in between the fulcrum and the effort. So my class 1 was having all the 3 characteristics: force multiplier, gain in speed, as well as change the direction of force. Whereas my class 2 will only and only work as a force multiplier. So my class 2 lever will only act as a force multiplier. Let's talk about, we have one more type of lever, and that is class 3 lever. Okay, so let's talk about class 3 lever. Now, how the class 3 lever looks like. So you will find that in class 3 lever, you will find that the pivot is at one end and there is a load at the other end. And most importantly, you will find that the effort is in between. The effort is in between the fulcrum and the load. Okay, so here again we will try to understand the different, the effort arm and load arm. So this distance from the fulcrum to the effort, this is my effort arm, and from the fulcrum to the load, this is my load arm. Okay, so you will find the difference. Okay, I will move back. I will show you the previous slide. Okay, see. So what we observe in class 2 lever, your effort arm is always going to be greater than the load arm, and so your MA and VR will be greater than 1, and it acts like a force multiplier. Copied? Okay. Okay. Chalo. So let's start with the next. What we were talking about here, class 3. So what we observe now? So we observe that this distance from the fulcrum to the effort is called as effort arm, and from the fulcrum to the load is called as load arm. So what we observe in class 3? So you will always find that in class 3 lever, the effort arm is less than the load arm. The effort arm will always be smaller because the effort arm is in between the fulcrum and the load. So your effort arm is less than the load arm, and then that's the reason why you will find your MA, your VR is always less than 1. So your class 3 will only act as a, it will only act as a gain in speed or speed multiplier. So your class 3 will only act as a gain in speed or speed multiplier. So a very quick summary of the topic. Class 1 lever, Class 1 lever will only can have all the three characteristics of a machine. My class 1 lever can act as a force multiplier, can act as a gain in speed, as well as it can act as a change in the direction of force. But when it comes to class 2 lever, my class 2 can only act as a force multiplier, and when it comes to class 3 lever, my class 3 lever will only act as a gain in speed. And if you want to remember the diagrams of class 1, class 2 and class 3, very simple. Class 1, remember that in the middle, in between, you will find in the middle, you will find the fulcrum. Means you will find the fulcrum is in between the load and the effort. Remember, the fulcrum is in between the load and the effort in class 1. In class 2, the load is in between the fulcrum and the load, fulcrum and the effort. In class 2, the load is in between the fulcrum and the effort. And in class 3, the effort is in between the fulcrum and the load. So remember what is in the middle. In class 1, fulcrum is in the middle. Not necessary. In between, I mean to say, not necessarily at the center. Okay. But in class 1, you will find the fulcrum is there in between the load and the effort. In class 2, you find the load is in between the fulcrum and the effort. And in class 3, you will find that the effort is in between the fulcrum and the load. So this is a very simple way to remember which one is class 1, which one is class 2, and which one is class 3. And more importantly, you also have to remember that my class 1 is having all the three characteristics, whereas my class 2 has only one characteristics, and the same is true with class 3. My class 1 can be a force multiplier, can be a gain in speed, can be change in the direction of force only. Whereas my class 2 will act only and only as a force multiplier, and my class 3 will only and only act as a gain in speed or speed multiplier. I hope class this idea about levers is very clear. If anyone is having any doubt, please ask or type your question. Please do it, because then we are starting with beta, please give me your responses. Okay, please say me whether you are getting it or not. Should I proceed? Because then I'm going to ask you all the questions now. From now onwards, it's your turn to answer the question. Whatever I have to make the ideas clear about lever, I have made it. Now it's your turn to respond. Okay, so please respond if anyone is having any doubt. There are around 21 students in the session, so I want all of them to respond to this. Okay. Beta, Mrugal, how will there be a gain in speed in class 3? See, understand, we have discussed that the MA is effort arm upon load arm. Okay, so if you look at with this principle, you will find that the effort arm is smaller and the load arm is bigger. So obviously smaller value divided by bigger value, your answer will always be less than 1. Okay, and if it is less than 1, then your machine works as a gain in speed. You remember yesterday and day before I have discussed, I had shown you all this. Yes, that what happens when it was working as a force multiplier. I told you this idea when I explained you in detail how MA is more than 1, how it is working as a force multiplier. When MA is less than 1, how it is working as a gain in speed beta. Okay, and again we are having this formula. With this formula also we observe that your load arm is bigger and effort arm is smaller. So smaller value divided by bigger value, your answer will always be less than 1. And if your MA and VR is less than 1, then it is a gain in speed. Okay, still you have any doubt, Mrugal, you can watch the videos of yesterday and day before where I have shown you how MA is, when MA is more than 1, how it is called as a force multiplier, or when MA is less than 1, how it is called as a speed multiplier. Okay, anyone else? Chalo. So I stop it here. Now I'm going to play another very fantastic video. Okay, I want all of you, I'm going to pause that video in between, and I want all of you to understand it. And please make a note of those points which is mentioned in the video. Okay. Can you see this video, bacha? Type, give your responses. Can you see this video?
Yes, sir.
Okay, chalo.
Suppose you wanted to move a large stone, but it was too heavy. One simple machine that could help is the lever. A lever can be any bar that tips back and forth on a point. The point is called the fulcrum. When you exert a force on one end of the lever, it produces another force here on the other end to lift a load. Suppose the load weighs 25 pounds. Then 25 pounds of force are needed to lift it. If the fulcrum is in the middle of the lever as it is here, you need to push down with the same amount of force, 25 pounds, on your end. If the load weighs 50 pounds, you need to push down with 50 pounds. The amount of force that you apply is the same as the force that acts on the load. The same force you'd need to lift the load without the lever. Notice what distances the two ends of the lever move. If you push your end down a distance of 2 feet, the other end moves 2 feet. If you move your end 3 feet, the other end also moves 3 feet. So when the fulcrum is in the middle, the force is the same at both ends, and so is the distance that each end moves. This lever makes your work easier only by changing the direction of force. It allows you to push down to lift something up. If you lift something directly, only your own muscles do the work. But when you push down, your weight can help you. Using your own weight as a force, with the lever arranged like this, you can raise something that weighs less than you do, but not something that weighs more. But suppose you move the fulcrum. Now you can lift something that weighs more than you. Why? The load arm, that's the length from the load to the fulcrum, is shorter than the other arm. And now, in order to get the load to move this distance, you have to move your force a greater distance. And in exchange, when you apply your force here, the lever applies a greater force here to raise the load. You trade increased distance at one end of the lever to get increased force at the other end. If you move the fulcrum even further, the load arm is even shorter. You move your force a still greater distance, but the lever applies a still greater force, so you can lift even heavier things. So here is a simple machine that can help you apply a lot of force where you need it. You often use a lever of this kind when you use a...
So class, just I want to highlight one thing what he said, very important, that what we are doing in machine, we are exchanging. Okay, so you observe that the force what we applied was for a greater distance, and what the force machine applied was more but for a lesser distance. Okay, so understand, in machines what we actually do, we do trading. Okay, so you can apply less force for a longer distance, and in turn the machine will apply more force for a shorter distance. Okay, remember this, I am repeating, what we do in machine, what basically we get from a machine, we can trade with machine, we can trade between distance and force. So what we can do, we can apply less force for a longer distance, and in turn the machine will apply more force for a shorter distance. Okay, so this is what basically is. Pay attention, listen to it, it's very interesting.
Tool. For instance, when you pry up dirt with a shovel, the dirt is the load. This point on the ground is the fulcrum, and you apply your force here. And when you pull a nail with a hammer, you're using another, only now the lever is bent. It still works the same way. The long arm travels a great distance, and the short arm produces a great force. The nail doesn't weigh more than you do, of course, but it would be extremely difficult to pull it out without a lever. You need the extra force. But there are times when increased force is not what you want, when you want to get increased distance instead. In that case, you apply your force here at the short end. You have to apply a large force, but that makes the other end move a large distance. Now you do the opposite of what you did before. You trade force to get distance, as you do when you row a boat. A short movement of your hands moves the other ends of the oars a long distance to move the boat. But using levers this way also gives you something else: speed. Both ends of the lever move back and forth in the same amount of time. But since this end moves farther in that time, it also has to move faster. So with this lever, you can make the boat move fast when speed is what you want. Now, suppose you take two of these levers and join them this way. That's how the levers are in scissors. The screw is the fulcrum for both levers. In these scissors, the load arms are longer than the other arms. So the force the scissors cut with is smaller than the force you apply here. Is there a way of getting these scissors to cut with more force? You can't move the fulcrum, but you can move the load. Now the load arms, from the load to the fulcrum, are shorter. The levers work as though these parts were no longer there. You know that the shorter the load arms are, compared with the other arms, the more the levers increase force. So the closer you put something to the fulcrum, the more force the scissors can apply, and the more easily they cut. Cutting and squeezing tools are made with load arms of various lengths. You can choose the one you need for the job you're doing. These shears, for instance, with the fulcrum near the middle, are good for trimming something easy to cut, like grass. If you need to squeeze something tightly, you might choose these. The load arms are quite a bit shorter than the other arms, so you can get quite a lot of force here. And if you need even more force to cut through a branch, for instance, you might choose these. The load arms are very short compared with the other arms, so these ends move through a great distance, and here you get very great force. But levers with the fulcrum near one end aren't the only kinds of levers that can multiply force. Some levers have the fulcrum at the end. To use this kind of lever, you could put the load here and apply your force at this end, in this case by lifting. Now, where is the load arm? The rule is that the load arm is always from the load, wherever it is, to the fulcrum. And the other arm is from you to the fulcrum. So in this lever, the two arms overlap. If you move your end a large distance, the load moves a smaller distance. And in exchange, when you lift with a small force here, the lever applies a larger force here. So once again, you're trading increased distance to get increased force. But notice that with this lever, both forces go the same direction. Suppose you made the load arm longer by moving the load toward you, and then even longer, and still longer. This way, the lever applies only a small amount of force. You supply the rest. Once again, the shorter the load arm is compared with the other arm, the more force the lever will apply to help you lift. You use this kind of lever when you use a wheelbarrow. This is the fulcrum. The closer you get the load to the fulcrum, that is, the shorter the load arm, the more the lever will help you, and the more you can lift. You use two of these levers together when you use a nutcracker. The best place to put the nut to get the most force is where the load arms will be as short as possible. But suppose you use this kind of lever a different way. Suppose you put the load at this end. Now this is the load arm, from the load to the fulcrum. In this case, the whole length of the lever. If you apply your force here, between the load and the fulcrum, then this is the other arm. You can see that now you have to apply a large force, but that the load moves a large distance. There are many levers of this kind in your own body. For instance, you use one when you swing your arm. From above, you look like this. Here is the load. Here is the fulcrum in your shoulder. And your muscle applies its force here. Your muscle pulls very hard, but only for a short distance, while the load moves a much greater distance, and with much more speed than the muscle. You use another of these levers when you lift something this way. Your elbow is the fulcrum. What you have in your hand is the load, and your muscle applies its force here. And when you bite, you're using another. Here's the fulcrum, here's the load, and here's where your muscle applies its force. So levers are simple machines that can have their fulcrums between the two ends or at one end. And depending on where you place the load and apply your force, you can use a lever to increase force or distance and speed.
I hope you have understood this, beta. Okay. Okay. So I hope you are getting this. What was the most important thing from this? Let me share a wide screen and let me explain you exactly what he was trying to explain. So understand what we do when we use a machine. Okay. Understand this. What we are doing. We have seen the three types of levers, and the most important thing is when we are using a machine, basically we are doing trading. What we are doing? We are doing trading. Okay, means I want less force for increase distance. What I want to apply less force for increasing distance, or I want to apply more force for decreasing distance. Okay. Means what? Whenever we use a lever, we see that my machine or my lever is working as a force multiplier. Okay. So when it is working as a force multiplier class, basically you are trading. What you are trading? You are trading it for less force for increasing distance. Okay. Let me give an example of it. Assume I have to apply 100 Newton of force for 1 meter. How much force I have to apply? I have to apply 100 Newton of force for 1 meter. Okay. So the problem is I cannot exert 100 Newton of force. Okay. So I will use machine. I will use a machine. I will use a lever. And what the lever can do? So lever, instead of applying 100 Newton, for applying lifting the object of 100 Newton to 1 meter, what I will prefer instead of that, I will prefer to apply only 20 Newton. How much I will prefer to apply? 20 Newton for 5 meters. Okay. Now, these are the two options. How much is the load? Try to understand. How much is the load in this case? So you will find the load is 100 Newton. How much is the load? 100 Newton. Okay. And how much is the effort? How much is the effort? Whatever the effort I am applying is 20 Newton. So you will find here my load is 100 Newton and my effort is 20 Newton. So if I find out the MA of this, you will come to know MA is nothing but load upon effort. So MA is load divided by effort. And how much is the load? 100 Newton. How much is the effort? 20 Newton. So how much will be the MA? The MA is 5. Okay. Now the MA is 5 means what? It means that this machine is multiplying the force 5 times. What the machine is doing? The machine is multiplying the force 5 times. But it's not that I am getting the advantage. I am definitely getting the advantage on force. Instead of applying 100 Newton, I have to apply only 20 Newton. So I am getting the advantage on force, but I am losing on distance because what the machine is doing, the machine is applying a force of 100 Newton for 1 meter. Clear? But what I am doing then in exchange of that, I am applying less force. But look at the distance for which I am applying. So I am applying the distance, I am applying that effort for 25 meter. I am applying the effort for 5 meter, whereas the machine is only applying it for 1 meter, whereas I am applying for 5 meters. So if you look at it, that you'll come to know that 100 Newton into 1 meter. So how much is the energy? How much is the work done? Work done or energy spent? Energy spent. Okay. So how much is the work done or how much is the input energy? So you will find the work done or the energy spent, okay, by me is energy work done or energy is spent by me is 100 joule because 20 into 5 is 100. So 100 joule. And how much is the work output, or we can say work input as well? And how much is the work output? How much is the work which is done by the machine? Work output. So you will find 100 Newton into 1 meter and you will again find it is 100 joule. Okay. So what we basically find, assume it's an ideal machine. So you will find that the work input is equal to work output. You remember the formula for work? It is force into displacement. Exactly. So here, how much is the force? 100 Newton into how much is the displacement? 1 meter. And here, how much is the force? 20 Newton. And how much is the displacement? 5 meter. So you find that this machine is working as a force multiplier, but basically class, what I am doing is a simple trading. I am trading for force for increasing distance. I don't want to apply 100 Newton. So I am ready to apply 20 Newton. But understand, when I'm applying 20 Newton means 1/5 of the load, I have to apply it 5 times the more distance. Okay, like let me give some set of examples. I have an option of applying, I have an option of using 100 Newton for 1 meter. Okay. I can apply a force of 100 Newton for 1 meter. Okay. Now, instead of this, this is what I have to do. I have to lift a load of 100 Newton for 1 meter. This is what I have to do. Now, this is the task. This is the task in hand. Now, how can I achieve this task? So how much is the energy required to do this task? So you will find the energy required to do this task is 100 joules. Yes or no? How much is the energy required? 100 joules. But then my options are, I can do it. Okay, these are my options. My options are, I can apply 100 Newton for 1 meter. That's the first option. Or I can apply 15 Newton for 2 meters. This is my first option. Or I can apply 25 Newton for 4 meters. This is my second option. Or I can apply 20 Newton for 5 meters. This is my third option. Or I can even apply 10 Newton for 10 meters. This is my fourth option. Or even I can apply 5 Newton for 20 meters. This is my next option. Or even I can apply 1 Newton for 100 meters. This is my next option. Now class, you say me which option will you prefer? Okay, you have to do this. You have to apply a force of, yes, very good, Saujanya. We have to apply a force of 100 Newton for 1 meter. But I have given you so many options. Which one you want to do? So you will say, sir, the last one. Saujanya just said, sir, I will prefer the last option. Okay. So if you prefer the last option, this one, try to understand that instead of applying 100 Newton of force, you are how much force you are applying? You are applying just 1 Newton. So instead of applying 100 Newton, you are just applying 1 Newton. So you will find, wow, I have to apply less force to do some heavy object, to lift some heavy object. Definitely you have to apply less force, beta. But in turn, look at what you are doing. So you are applying 100 Newton, but you are applying 1 Newton, but for 100 meter. So what you are doing, you are ready to apply 100 Newton for 1 meter, and in turn, what the machine will do? Machine will apply 100 Newton for 1 meter. Getting it? So basically what you are doing, you are simply exchanging. You are simply exchanging. So understand, your machine, understand, any machine can be a force multiplier. Yes, a machine can be a force multiplier, right? Can a machine be a gain in speed? Right. Okay. Can a machine be the change in direction of force? Right. But can be a machine be work multiplier or energy multiplier? And the answer is no. Understand class, my machine can be a force multiplier, can be a gain in speed, but no machine is ever a energy multiplier, because the input energy and the output energy is same. What basically we are doing? We are simply doing the trading. Instead of applying 100 Newton for 1 meter, what I am doing, I am using a machine, and in that machine, the machine will apply, means I will apply 1 Newton now for 100 meters, and in turn, the machine will apply 100 Newton for 1 meter. So basically, if you look at the input energy, how much is the input energy? So you will find the input energy here is coming out to be 100 joules. 1 Newton into 100 meter input energy. How much? 100 joule. Or how much is the work done on the machine? 100 joule. And how much is the work done by the machine? So the work done by the machine is also 100 joule. 100 Newton into 1 meter. So basically, we are just trading. We are simply, whenever we are using a machine, whether for a force multiplier or a gain in speed, we are simply doing the trading. I am trading force for distance or distance for force. All of you class, are you getting this idea of machine? My machine can be a force multiplier, can be a gain speed, but my machine can never be a energy multiplier. Look at the input energy and look at the output energy. In the both the cases, you find the input energy and the output energy is still the same, whereas I am getting the advantage of force. So as I'm getting the advantage of force, I'm losing on distance. All of you, are you getting it, beta? Please give me a response. Okay, because that's very important, beta, that you should understand it. Okay, please, all of you, there are so many students. I want all of you to give the response. Okay, okay, chalo. Thank you very much. Okay, so I stop sharing this.